Okay, you guys can go ahead and get your PowerPoint back out. We're going to finish section 5.2. You're all pretty much in the same area, so we're just going to get started right here. We talked about action potentials. If you remember, action potential is just a nervous impulse that sends an electrical signal. So you guys, page 164 is kind of where we were. There's a really good picture of the synapse. Remember, acetylcholine is a neurotransmitter. That means it's a small chemical that transmits a neurological message, or that stimulus across that space. If you'll notice in this picture, those little green kind of look like little pills or something, those are acetylcholine. And that transmits to the muscle, and that's what causes what's called a depolarization in the muscle cell. Okay, so depolarization is where you basically have a change of the charge of a cell. So what happens is this acetylcholine gets into the muscle fiber, which causes its sarcolemma, which remember is its plasma membrane, to basically become permeable to sodium. So sodium rushes into the cell, and at the same time, potassium is being pumped back out of the cell. But sodium's rushing in so fast that it changes the charge of the muscle fiber itself, and that's what causes that action potential, or that nervous impulse, to shoot across the muscle cell, makes it contract. So that's what an action potential is. Depolarization just means it's that changing, that flipping of the charge of that so that it can do what it's supposed to do. Okay? So if you'll look at this picture, okay, this is a picture of a sarcomere, and a sarcomere is like an individual contracting unit within the cell, okay? These are not made of cells, these are inside each muscle cell. And it looks like this little unit. So it says glucose is stored in the form of glycogen within the muscle cell, provides energy for creating this action potential. Okay, actin and myosin, that's this, okay? Actin is this purple, purple filament. Myosin is this red one on here, okay? This is what actually works, proteins that contract, that cause contraction of that muscle. This whole little unit is called a sarcomere. So basically what happens is the action potential occurs that sodium rushes in, it changes the charge of that fiber, okay? And when it does that, it triggers this myosin and actin to contract. So this myosin, these little heads on the end of this myosin, basically kind of reach up, grab onto this actin and pull it down. It just kind of like reaches up and grabs it and pulls it together. And that's what makes it contract. Okay? Now, you know, we talked about how skeletal muscle cells, when you look at them under the microscope, they have striations. Okay, what gives muscle cells the striations is the presence of the sarcomeres. So this little kind of blank area in here is what causes those little lines that you see on the muscle cells. Really cool. That's what causes it. Okay, so that's the individual contractile unit inside the cell. So we're talking tiny, 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 tiny. All right, maximum tension and then a return to relaxation. It says when receiving an action potential, a given motor unit always develops a maximum tension. It says all or none law. What this means, it says, well, because each whole muscle includes multiple motor units, simultaneous activation of many motor units is required for the muscle to develop maximum tension. Okay, so you need more motor units than just that one to really make your whole muscle contract. Okay. It says this diagram at the bottom kind of explains the tension that's developed in response to a single stimulus. It kind of works on, well, no, I better not say that, but it's, you know, it gets more stronger and stronger and stronger the more the motor units stimulate it. It says with high frequency stimulation, the muscle develops a sustained maximal level of tension called tetanus. We're not necessarily talking about the disease tetanus. We're talking about that. And finally, if you think about lifting something that's really heavy, okay, and you lift it, and you're using all your muscles to the point that you can't use them anymore, that's what it's talking about. says almost all skeletal motor units develop tension in a twitch-like fashion, generating maximum tension very briefly and then immediately relaxing. So it's like tense up and then let go, tense up, let go. But because there's so many motor units in one muscle, okay, there's so many motor units in that one muscle, they have different ones firing at different times. So it gives you that strength. It says after the action potential has traveled the length of the muscle fiber, so it goes all the way down, chemical processes return the fiber to its resting state. So it flips it back over, makes that sodium get pushed back outside, pulls the potassium back in. Sodium ions diffuse back out of the cell into the interstitial fluid, and then calcium ions return to storage sites within the cell. The actin filaments slide back to their original positions, and then it relaxes. Okay. That's kind of the very, very, very basics on how your muscles actually work. Okay. Okay, skeletal fiber types. It says, why are some athletes especially good at events or tasks? I'm on page 165, by the way. Whereas others excel at activities that require explosive strength or speed. So, sprints versus long distance. And some people are better at different ones. Thus, the answer may have to do something to do with the way in which their individuals train, but that's only a small part. It says, in fact, a big part of why certain people are better at particular activities in sports may relate to the characteristics of their skeletal muscle fibers, so depending on their muscle fibers themselves. So skeletal muscle fibers may be divided into two categories. You have slow twitch and fast twitch. Okay, fast twitch, okay, obviously tend to contract faster. And then there's two different types of those. You have type 2A, that's like an intermediate quickness, and then type 2B, and those are the very fastest. That's on your PowerPoint there. But typically the faster they contract, they also fatigue faster. Okay, that's why you can't run a sprint. You can't run a sprint for a whole mile. Okay, because you get fatigued much more quickly with those. So it's pretty interesting. This little, I would encourage you guys to read the little blue section on page 166. All right, let's look at the architecture. So how the muscles are structured in relation to how they function, okay? So parallel fiber arrangements, parallel fibers, okay? So hear that, means they're all parallel, they're going in one direction, right? So look at these different ones. You have fusiform, okay, this is kind of like bicep, or triceps. Bundled, which is like rectus abdominis, okay, and then triangular, and you've probably seen this one. This looks like the deltoid. Okay, pennant fiber arrangement says these attach obliquely, doesn't necessarily shorten as much, but it can hold more fibers. So that's something to note as well. Each fiber attaches obliquely, so it can go sideways. It attaches to the side of a tendon, if you will. Think of it that way. And sometimes attaches to more than one. So unipennant would be that it's got one, right? See, look how it attaches on either side of this. And then multi, it's got multiple ones there. So certain muscles of the hand are unipennant, and the rectus femoris, member of the quad and the thigh, okay, is bipennant, and then the deltoid is actually multipennant. There you go. I said deltoid on the triangular one. I was wrong. I should have read my examples in here. Biceps is fusiform, rectus abdominis. Oh, pectoralis major is an example of a triangular one. There you go. Okay. Okay, muscular strength says rotary force that muscles can produce at a joint. So usually when you're measuring your strength and you're using weights, it's joint related. So how strong is your muscle to move that particular joint? Okay, another word here, is torque. It says it's the product of the size of the force from the axis of the rotation. Okay? Torque is the product of the size of the force from the axis of rotation. The maximum weight you can lift is a measurement of muscular strength, but it's really hard to be accurate for a single muscle. You know, you think about it, even if you're doing, you think about doing bicep curls, okay? You know, you're not just using your biceps, you're using your forearms, right? You're using your back, you're using your lats, you've got everything. I mean, you're using more than just your biceps. Okay, good. Okay, muscular power. So it's a variable that does involve speed is muscular power. So when you're looking at your strength, you're not necessarily talking about speed, right? If you're trying to lift as heavy a weights as you can, you know, you're trying to max out, you're not doing a bunch of reps, right? You're maxing out, you're trying to do as much as you can, okay? But power includes speed in with it. So it says mechanical power is defined as force multiplied by velocity. So muscular power then, specifically it says is muscle force multiplied by muscle shortening velocity during contraction, okay? So it's usually, again, several different muscles together. All right, oops. Endurance, okay? So muscle tension or time says how far you can run is a measurement of muscle endurance, right? How quick does it fatigue? And you guys, we're going to do a lab actually next week on muscle fatigue, and you're going to get to see how quickly your muscles do fatigue. Okay, it's the ability of a muscle to produce tension over a period of time. So typically, obviously, the longer the activity, the higher the endurance. And then the fatigue is when it reaches its point where it just can't go on. So some things that can affect fatigue, you've got the work itself, whatever you're doing, that thing itself can affect fatigue depending on how strenuous it is, how often the muscle is used, right? If you do the same exercise every day over time, you develop endurance in that muscle or in that muscle group, right? So it can handle more. Composition of the muscle itself, and then, of course, the environment. You know, the more oxygen, the better you're going to do. Less oxygen, less you're going to do. How available, you know, what kind of temperature is it, and how does that affect things like that. Okay, I'm not, there won't be a ton of questions on that last little bit about the strength, power, and endurance. But I do want you to, that's it. You just need to, you might read that section again, but it's important that you still get that one. So I want you guys to, lost my train of thought there. But anyway,